we continue our discussion on error analysis, and then we will wind up today with discussion on dimensional analysis. In the last lecture, we had seen all the rules about significant digits and how we account for these. Let us have a look at this with the help of some problems. So, we start with directly with some problems. Let us say we take problem number 1, where it is given that mass of a box is given as 2.3 kgs and 2 marbles of mass 2.15 grams and 12.39 grams are placed in the box. And the question is, what is the total mass of the box correct in up to the number of significant digits. In a problem like this, what we have to do is we have to look at all the individual quantities and we find the number of significant digits in each of these, and we use the rules which we have seen, and if I repeat them, if we are adding or subtracting quantities, then we go to the number of decimal places which are there in the least accurate measurement, or which has the least number of decimal places, and the final answer has to be put in terms of that many number of decimal places. Whereas, if we are using a multiplication or division, then we count the number of significant digits. So, here now when we look at this problem, we realize that the units which are given are different. So, the first thing which we have to do is convert everything in the same units. So, let us work this out. So, this mass which we have, we convert everything to kgs. So, the total mass of the box plus the marbles. So, let us look at the original problem. The mass of the box was 2.3 kgs and the marbles were 2.15 grams and 12.39 grams. So, when we add this, we will get this as 2.3 kg plus we convert 2.15 grams into kgs. So, this becomes 0.00215 kg, and the third one, which has 12.39 grams, will become plus 0.01239 kg. And when we add all of them, we get our answer as 2.31454 kg. And now we have to work on significant digits. Here what we see is the first quantity which we have added, 2.3 kgs, is correct is given up to 1 decimal places, whereas the other quantities are going, this one is going up to 5 decimal places, both of them are going up to 5 decimal places. So, we have to round up our answer up to the first decimal place. So, this is 2.314. So, in terms of significant digits, we will write the answer as 2.3 kgs, which looks in some sort of an error, it looks wrong, because the box itself was 2.3 kgs, you have added 2 marbles, but the answer has not changed. And the reason for this is that the mass of the box which was given to us was given correct up to 100 grams, 0.1 kgs, and both these marbles are much less than 100 grams, and even their total mass when you add them up is less than 100 grams. So, therefore, this does not affect. Now, we make a small deviation to the question. Suppose if the mass of the box was given as 2.300 kg, how will this answer change? And here you have to realize, now when you say the mass of the box is 2.300 kgs, that means it has been measured correct up to 0.001 kg. So, we have to go up to 3 decimal places here. So, in the final answer which we look at, we have 2.31454. We have to go up to 3 decimal places. So, therefore, now we have to go 2.314. Now, the next digit is 5 followed by a 4. So, therefore, when we round it up, this will become equal to 2.315 kg. So, this is how the answer will change if the original data which is given to us becomes 2.300 instead of 2.3. And this is the type of care one has to take when we do things in error analysis. Now, let us take one more problem which talks of this, and because of change in units, we have to ensure that we have to match units. So, let us say that two lengths L1 and L2 are measured, and they are given as L1 is equal to 9.99 meters and L2 is equal to 9.99 mm, and we have to find the sum in up to correct significant digits. So, sum has to be found out. So, once again we have to be careful, we convert both to same units. So, L1 is equal to 9.99 meters and L2 will be equal to 0.099 meters. We convert, we divide this by 1000. So, this is what we will get, and now when we add up the two, we get L1 plus L2 is equal to 9.9999 meters. So, now in the two we have to go up to the least amount of significant least amount of decimal places. We see this one in meters is up to 2 decimal places, whereas L2 is in meters is up to 4 decimal places. So, we have to finally write our answer, if we write it in meters, correct up to 2 decimal places. So, this will be equal to, so now if I have to round it up to 2 decimal places, it is 9.99, but then it is followed by a 9. So, the rounded up answer will be equal to 10.00 meters. Now, you could have also converted this in millimeters and done the same thing, you would have got the same answer. We take an example which involves multiplication. So, let us look at this problem. Suppose it is given each side of a cube is equal to 5.402 centimeters, and we have to find surface area of the cube in appropriate significant figures. Now, since the data is given to us in centimeters, we will find the answer in centimeter squares, but when we find, let us write the formula for surface area is equal to 6a square, which means now a multiplication is involved. Since a multiplication is involved, the final answer has to have the same number of significant digits as the original given data. Now, in the given data, number of significant digits is equal to 4. So, the final answer also we have to write up to 4 significant digits. So, now let us see, if I calculate 6a square and I do the exact calculation, maybe using a calculator, I will get my answer as 1.75.0899624 centimeter square. And this is the point which we are saying, I do not need to express the answer in so many decimal places, because our original data is correct up to 4 significant digits. So, now if we have to, so my number which we have is 175.089624 centimeter square, and this we have to write correct up to 4 significant digits. So, this will be equal to 175 point. Now, 0 is the 4th significant digit. I see it is followed by 8. So, therefore, I round it up to 175.1 centimeter square. So, this is how one accounts for significant digits when we do problems involving multiplication. Now, let us look at a problem which involves or use of all the formulas which we have learnt, and what we have in the problem is to determine the acceleration due to gravity g. One uses the formula for a time period of a watch which is equal to 2 pi times square root of 7 times r minus r by 5 g. This time period is possibly of some pendulum or some swinging body, and this formula is given to us. So, now what is also given is that the value of r is the measurement is given as 60 plus minus 1 millimeter. The value of small r is 10 plus minus 1 millimeter, and to find the time period, the experiment is repeated 5 times with a watch, and the time period is measured. The time period which is measured in the 5 experiments are given as 0.52 seconds, 0.56 seconds, 0.57 seconds, 0.54 seconds and 0.59 seconds, and the least count of the watch is given as 0.01 seconds. So, given all this data, what we have to find is, we have to find the percentage error in the measurement of small r, t and g. Basically, we have to find the percentage error in g, but we will need r and t. So, therefore, we look at all these quantities also. So, what we do is, we look at the first, the value of t is given to us as repeated experiments. So, we calculate the mean value of t of the time period, and we add up all the 5 given data, divide that by 5. So, we get the answer as of t mean as 0.556 seconds. But we realize the original data is given to us correct up to 0.01 seconds. So, we will round up this 0.556 up to the second decimal place. So, 5 is followed by a 6. So, t mean will become 0.56 seconds. This is an important step, that finally you have to take the mean value as the one which has the same number of significant digits as the original data. Now, to find the percentage error in t, let us calculate the individual error in each of these measurements. So, we have in the first measurement is 0.52, 0.52 minus 0.56, this is minus 0.04, we take the absolute value, it is 0.04. For the second measurement, we will take 0.56 minus 0.56, so delta T2 will be 0. Third measurement 0.57 minus 0.56, so that will give us 0.01. Fourth measurement will give us 0.02, and similarly the fifth measurement if we do, that will give us 0.03. So, we calculate the mean error. The mean error is the sum of all these divided by 5. So, we get that as 0.1 divided by 5 is equal to 0.02. Now, here the answer which we have calculated is coming up only up till the second decimal place. Suppose if the answer which we got was up till the third or fourth decimal place, then we should have rounded it up to the second decimal place. We do not need to do this here. So, now once we know the mean error in t, the percentage error in t will be delta t by t into 100, which is 0.02 divided by the value of t, which is t mean. So, divided by 0.56 into 100, and when we calculate this percentage, it comes out to be 3.57%. If we want to find the percentage error in small r and capital R, so we go back to the data. Small r is given to us as 10 plus minus 1 millimeter. So, the percentage error in this will be in small r will be there is 1 divided by 10 into 100, and this is equal to 10%. So, this is the error in small r. Now, to find the error or percentage error in G, we first write the formula for G. That means, the formula was given to us in terms of time period, we square that to get the and write the formula in terms of G. When you do that, you will find G comes out to be 28 pi square upon 5 times r minus r by t square. Once we have this, then we use our error analysis, we write delta G upon G. The change in error will be equal to, now 28 pi square and 5 are constants. So, therefore, there is no error in this. That means, we have to account for error in r minus r and t square. So, this will be equal to error in r minus r divided by r minus r plus, now there is a t square. So, 2 times delta t by t. Now, if you realize the rules, what we had seen, whether it is multiplication or division, we always add up the relative errors. So, this is delta G by G. Now, let us work out the error in r minus r. This is a quantity which is a sum or a difference, r minus r. So, error in r minus r will be equal to delta r plus delta small r, and delta r was given as 1 millimeter, delta small r was 1 millimeter. So, the total error in r minus r will be 2 millimeters, and r minus r was given as 60 minus 10. So, this is 50 millimeters. So, we will put this in. So, delta of r minus r by r minus r will become 2 by 50, and then we have 2 times delta t by t, which we have already calculated. So, that becomes equal to 2 times 0.02 by 0.56. This gives us the relative error in delta in the value of gravity. Now, if we have to obtain a percentage of this, then we can multiply by 100. So, we multiply both sides by 100, delta G by G into 100, we will get it as this is first number will become 200 by 50, second number which we had calculated was 3.57. So, we multiplied by 2 and multiplied by 100. So, we get 4 plus 7.14. So, the percentage error is 11.14%. So, in this example we have seen how we account for errors when in the formula, if you have a sum as well as a product or a division, how we take care of errors. The first we calculate the individual error in the quantity in the part of the formula where the summation comes. So, therefore, the 2 errors in the quantities which are summed are added up, and then we find the relative error in that quantity, and the second quantity which is a division of this. So, therefore, we add the relative error to that, and this is how we calculate all the errors. Now, let us have a look at dimensional analysis. What we find is that all the quantities which we measure, all quantities can be expressed in 7 basic dimensions, and it will turn out that maybe all of them do not need the 7 basic dimensions. And these 7 basic dimensions which we choose: length, mass, time. These are the 3 basic dimensions which will come in most of the mechanics problem. Problems involving classical mechanics will normally have only these 3 dimensions. Once we come to electricity, then we get a dimension which we use A, and that is the sign for current, and for temperature we can use a symbol K to differentiate it from time, or sometimes people also use Greek symbol theta for temperature, and then sixth quantity will be intensity, and we can use this is luminous intensity. In SI units, the symbol used is cadilla, so we keep cadilla, we can use anything else also. And finally, the amount of quantity in a substance, which will use moles, so we can use MOL. So, these are the 7 basic dimensions, and any quantity which we write can be expressed in terms of products or divisions of these dimensions. Now, it is not sacrosanct that we take only length, mass and time as the basic dimensions. Somebody else can take force, mass and time as the basic dimension, and that would also be valid, but then if we use force, mass and time, then length cannot be taken as a basic dimension. And the rule is that within these basic dimensions, we cannot form quantities which can be made from these dimensions itself. As an example, let us see, if I look at area, then area is equal to length square. So, either I can use area as a basic dimension or length, but I cannot use both length and area as a basic dimension, because they can be obtained from each other, that means they are not independent. So, given these basic dimensions, we can use some analysis, and that can be of use. So, we have one thing which we have to be careful about when we write our equations. All our equations which we write in physics, they should have dimensional consistency. And the meaning of dimensional consistency is that quantities of same dimensions can be added or subtracted, which means if two quantities are added or subtracted, or I say A is equal to B, then quantity A must have the same dimension as quantity B, and this principle has to be followed. So, for example, we cannot add force and velocity, because the dimensions of force will be mass times acceleration. So, if we express it, it will be m times L by t square, whereas velocity will be L by t. So, one of the first things which you have to do when you do problems involving dimensional analysis is that for quantities other than the basic dimensions, you express them in dimensional terms as a function of the basic dimensions. And this you will be able to do very easily if you remember the formula for some of the quantities. We have not seen some of them, but you may have seen them in earlier classes. For example, when we talk of speed, then the dimension of speed, normally we use a square bracket when we want to write. This is equal to, speed we know is distance upon time. So, the dimension of this will be equal to L by t, and this we express as L times t to the power of minus 1. And we do this for all the other quantities which we have. So, for example, force which we talked of. So, force is equal to, you may remember from your basic from earlier classes, force is given as mass times acceleration. So, the dimension of force will be equal to mass times the dimension of acceleration, which is equal to L by t square. So, this we will express the total dimension of force as m times L times t to the power of minus 2. So, any new quantity which you come across, you should be able to write the dimensions of that in terms of the basic dimensions. Now, how do we use dimensional analysis? As we said that all terms in an equation which are added or subtracted have the same dimension. So, this is called the principle of dimensional homogeneity. All terms in the same equation which are added or subtracted have the same dimensions. And when I say added or subtracted, this also leads to things like A is equal to B, because this can be seen as A minus B is equal to 0. So, therefore, both A and B have to have same dimensions in an equation. So, now what one can do is, if I know, if I am given an equation as we had seen in the previous example where we had seen there was a formula which was given to us in terms of time period, that we had seen this in the problem, t is equal to 2 pi root of 7 times r minus r by 5g. So, if this formula, one of the ways one has to ensure is that the left hand side dimension, which is the dimension of t, must be equal to the dimension of the right hand side, where we have constants which are dimensionless like 2 pi 7 and 5, but then we have r minus r by g. So, dimensionally both sides have to be consistent, and this dimensional consistency of equations is what one can use, and this is what gives us also the how dimensional analysis can be used to predict some formulas. But one thing we have to ensure, one thing we should realize, or the catch is, while dimensional consistency is necessary, that means two terms in the equations have to have same dimensions. Dimension of A is equal to dimension of B if A is equal to B. But just if dimensions of A and B are equal, it may not ensure that A is equal to B. It is just a way to check the first step. Dimensional consistency does not guarantee that the formula is correct, but if dimensional consistency is not there, the formula is wrong. So, dimensional consistency does not ensure that formula is correct. The constants which are there, they may be wrong, but if dimensional consistency is absent, then clearly the formula or equation is incorrect. So, this one has to take care, and also what we realize is that there are certain quantities which are dimensionless, and using dimensional analysis we cannot do anything about the dimensionless quantities. Example of dimensionless quantities: first one is angles. All angles which we measure, they are dimensionless. Or we could have ratios of similar physical quantities. So, if you divide one quantity by the other which have same dimensions, the resulting quantity will be dimensionless. And an example of this is the refractive index. The refractive index, when you calculate this, is dimensionless because it is the ratio of the distance travelled by light in two different media. So, therefore, this will be a dimensionless quantity. So, how does then one use dimensional principle of dimensional analysis to work out quantities? And let us look at this with the help of some example, and we will see how we can predict certain formulas. Let us see, it is given to us that time period of vibration of a drop depends on surface tension S, its radius r, and density rho of the liquid. And we want to find out an expression for the time period. So, time period, let us say t we put it. So, we want to find an expression for t. So, here what we will do, the way we express these problems. Now, one thing we will have to realize, this will work when we are talking of time period is a function of surface tension, radius and density. So, if we write the basic dimensions which are involved in all these quantities, then we will see time period will involve time. Surface tension is a quantity which is force per unit length. So, it will involve all mass, length and time. We will work it out. Radius involves only length, density involves mass and length. So, totally we see 3 basic dimensions are involved here, m, l and t. So, here time period is a function of 3 other quantities S, R and rho, and at best we can get our formulas. If there are 4 quantities and 3 basic dimensions, then the 4th quantity can depend at most on 3 other quantities. If it depends on 4 or 5 quantities, then we cannot get a formula using dimensional analysis. And we have to look at the number of independent variables which are there, and that is what will give us. Sometimes the number can be even less. So, let us first solve this problem. So, we want to find, so the way we work this out is we assume that the time period t is proportional to s to the power alpha, r to the power beta, rho to the power gamma. Now, here alpha, beta, gamma are unknowns, and these values we will be able to get using dimensional analysis. And how do we do? So, we work out the dimension of each of these. The dimensions of the time period t, this we write, this will be equal to just, we write it as L m t. For each quantity we will express the things in terms of L m t, and if none of the quantity is involved, we will put it as power 0. Now, dimension of S, this is, and this is how you work this out, this is force per unit length, surface tension. So, this will be equal to force we have seen is mass times acceleration, and then we have a length. So, this when we work it out, this will be equal to, we see both the L's go away, m times t to the power minus 2. We express things in terms of negative powers, and then we have r, dimension of r will be just length. So, that will be equal to L times m to the power of 0, t to the power of 0. If you want, you can, for ease of calculation, maybe you can just write it as L, and in the final expression when you write, you carry all L m and t. And now, rho, the dimension of rho, this will be mass per unit volume. So, this is mass divided by volume. So, rho can be written as m by L cube. So, the dimension will be m times L to the power of minus 3. So, now when we finally express this, what we get is L 0 m 0 t to the power of 1. This is equal to m times t to the power of minus 2 to the power alpha, L, this is the dimension of r, and m times L to the power of minus 3 to the power gamma. Now, here this is the dimension of S, this is the dimension of r, and this is the dimension of rho. Now, we calculate. So, we now equate powers of L, M, T separately. This will give us 3 equations, and that is why I said we cannot, if there are more than 3 quantities, then we will be just be able to reduce the number of variables, we will not be able to give the final form. So, here let us do this. So, now when we write this, we get L is to the power of L is given as 0. So, we get 0 is equal to beta minus 3 gamma. This is what L gives us. Next we go to M. M will, again the power of M on the left hand side is 0, is equal to alpha plus gamma. And then we have the third quantity, which is T. So, here we have 1 is equal to minus 2 alpha and nothing else. So, first we solve this equation, this gives us alpha is equal to minus half, and then we go to the second equation, we get gamma is equal to half, and then we go to beta, the third equation, beta is equal to 3 gamma. So, beta will be equal to 3 by 2. So, now we go back to the original equation. Our original equation was T is proportional to S to the power alpha, R to the power beta, rho to the power gamma. So, this now we can write T is equal to K times S to the power minus half, R to the power 3 by 2, rho to the power half. And if I write it in terms of the usual expressions, I will get it as K times square root of R cube rho upon S. So, I can derive a formula like this using dimensional analysis. Let us look at another problem, a second problem, where the problem it is given to us is potential energy of a particle varies with distance x from the origin as, and the formula is given to us, u, which is the potential energy, is equal to a times square root of x divided by x square plus b, where a and b are dimensional constants. And the problem says find the dimensional formula for AB. What we mean by dimensional formula is the dimensions of AB in terms of the basic dimensions. So, here that means to find the dimensions of AB, we have to find dimensions of A and dimensions of B. So, let us look at the original formula. Now, here we have u is equal to a root x by x square plus b. So, how do we find the dimensions of b first? Let us find the dimensions of b. We see b is added to x square. So, if this formula which is given to us has to be correct, then the dimension of b has to be the same as the dimension of x square. So, because we have x square plus b, this implies dimension of b is equal to dimension of x square. So, this means dimension of b will be equal to L square, because x is a distance, it is given distance x from origin. So, therefore, it is length. Now, we look at we want to find the dimension of A. So, we invert the formula. The formula is given to us for u. So, we now write the formula in term for A. So, A will be equal to u times x square plus b divided by square root of x. So, therefore, the dimensions of A, now if I write the dimension, this is for A. So, A is given like this. So, dimension of A is equal to dimension of u times dimension of either x square or b, one of these. So, let us say dimension of x square divided by dimension of square root of x. Now, what we need to find is the dimension of u. U is given to us as potential energy of a particle. Potential energy as, and now when you do not know some of these quantities, you may initially have to start by just remembering dimensions. But once you know what all these quantities are, then remembering, you do not need to remember dimensions. Potential energy, if you recall, either we can say it has the same dimension as kinetic energy. So, it is mv square, or we could think of potential energy as mgh, and using whichever way we get the dimension of energy as dimension of mass times v square. So, this will be equal to m times L, v square will be L square t to the power of minus 2. So, this is the dimension of u. So, now from here when we have to work out the dimension of A, let us do that. So, dimension of A will be equal to dimension of u. So, dimension of u is m times L square t to the power minus 2 times the dimension of x square, dimension of x square which we have here. So, let us just write this. So, dimension of x square will be L square, and then we have divided by square root of x. So, this will be L to the power minus half. The minus comes because we have taken it in the numerator. So, this way we work out, and when we write this, the dimensions now we write. So, the dimension of A turns out to be equal to m times L to the power of, we have 4 minus half. So, L to the power of 7 by 2 t to the power minus 2, and then we have to find the dimension of A times B. This will be equal to m L to the power 7 by 2 t to the power minus 2 times B, which is L square. So, the final answer we get is m times L to the power of 11 by 2 t to the power minus 2. So, these type of problems which are there, they are basically quite simple. Now, I would like to give an anecdote. It looks like dimensional analysis, how can it really be useful in life? And just in World War II, toward the end of the war, America was doing some experiments on nuclear bomb, and they were very classified data. And those experiments were being carried out in Los Alamos labs, and what they had done was they did not release the energy of the explosion which was coming out, because these were nuclear explosions which were being done there. But what they did was they released the photographs of those explosions along with the time period at which the front of the bomb, which was of the explosion, was moving. And G.I. Taylor was a renowned person, renowned scientist in UK at Cambridge. He was a mathematician, and what Taylor did was, Taylor from the pictures of those explosions, how the wavefront was travelling, was able to estimate the energy of the explosion using what we have done, dimensional analysis. So, a simple dimensional analysis was used to actually get a lot of classified data which was otherwise not given, and it sort of Americans were found blushing after that, the scientists, because they thought they had only given the photographs of the explosion. But using dimensional analysis, Taylor was able to predict some of this sub the data of the energy of the bomb from the wavefront speed. Now, there are certain limitations of dimensional analysis. It is not that dimensional analysis alone is able to give you everything. Let us look at some of the limitations. Well, one limitation is two physical quantities which are not related can have same dimensions. And as far as dimensional analysis goes, it will treat both the quantities as same. And let us give a very simple example of this. When we talk of moment of a force or torque, this is a dimension of force times distance. And when we look at, so this is quantity A, and the second quantity which we look at is, let us say, the kinetic energy or work done. These also have the same dimensions as force times distance, whereas these two quantities physically are very, very different. One gives us the turning effect of the force, the other gives us the energy or the work done. But if we use dimensional analysis, it will treat both of these quantities as same. Then secondly, as you must have realized, we got a formula up to the formula which we get from dimensional analysis are correct up to a constant k, which is dimensionless. Now, dimensional analysis cannot help us in finding the value of k. So, using dimensional analysis, we cannot find the dimensionless constants which come. The third limitation is that we cannot use dimensional analysis to predict behavior where equations have quantities other than powers of products, because using dimensional analysis, as we have seen, we can only relate things which have powers of products. So, for example, if we have a formula y is equal to y0 sin omega t, we cannot get sin omega t from dimensional analysis. But one thing dimensional analysis can tell us is, because sin has a argument which is an angle, then omega t by itself has to be dimensionless. But we cannot get a form like sin omega t from dimensional analysis. Or even if we have a formula like which we will encounter in mechanics as S is equal to ut plus half a t square. Now, a formula like this cannot be obtained from dimensional analysis. But what dimensional analysis again in this formula can tell us is that ut and S have to have the same dimensions. Similarly, half a t square and S have to have the same dimensions. But we cannot predict this form ut plus half a t square from dimensional analysis. And for those of you who are more interested, what we will realize is that this dimensional analysis, as we have seen here, this is a limited form of what is called the pi theorem of Buckingham. There is a Buckingham pi theorem, and what we have seen here is basically a limited form of this theorem which we have done here. Because as we have seen, if there are three basic dimensions in a problem, then we can only find relations up to 4 variables at most, and sometimes even that may not be possible if there are only 2 basic dimensions appearing, or if in some combinations the dimensions cancel out. See, for example, there is a formula for a frequency of tuning fork. The formula for frequency of tuning fork in some conditions is given as frequency is equal to d by L square times V. Now, a formula like this cannot be predicted by dimensional analysis, even though we have 3 quantities on the right hand side and 1 quantity, totally there are 4 quantities. And here if you realize the reason why this does not work, why dimensional analysis cannot be used to predict this, is because there are only 2 basic variables L and T in this. So, that means at most 3 quantities we could have derived this formula. So, this formula cannot be derived from dimensional analysis. So, we should not go by just blindly counting the number of variables. Number of basic variables here are only 2, L and T. So, therefore, we could at most get 3 variables involved, but there are 4 variables F, D, L square and V. So, therefore, but once again the dimensional consistency has to be ensured. The dimension of F has to be the same as dimension of D by L square times V. So, that dimensional analysis can check. So, this is how we see, while dimensional analysis is a powerful tool, but it has its own limitations.